So yeah, I'm excited, super excited that Nasrin is here today to give us a talk about common sense. As many of us know, she was really among the most influential people who led the research into common sense. Many of our papers actually from UW and AI2 also made use of her rock story corpus. We just call it as a rock story corpus, but I think it may have meant like Rochester MSR common sense story corpus. And so, yeah, that was really enabling resources for many of the follow-up work. And then Nasrin also worked on, if I remember right, like image-based common sense research as well, like having a dialogue about it or asking natural questions. And I remember seeing all these papers back then thinking, wow, like, how do you work on all these questions early on? And so, and then last year, it's already last year, she had this really amazing paper, Glucose, that also received the honorable mention at best paper honorable mention at EMNLP. So I assume it's going to be about that. But in any case, she was, after PhD, she was at Elemental Cognition, the startup company, I think, at New York City, that also studied common sense. But now recently, Nasrin started a new startup company, Vernic. So that's also really exciting news. Anyway, so take away, Nasrin.
Thank you so much, Yejin, for such a nice introduction. And yeah, hi, everyone. Glad to virtually see you all. I was just telling the initial people on the call how much I miss like doing this in person with people. Is often one of the fun parts of doing talks, just getting to see new people and chat about the ongoing research. So I'm looking forward to getting somehow a dynamic talk here. I know it's hard to sort of interact and interrupt on a Zoom call. Like, sorry, I'm glad you guys are not using Zoom, by the way, on a video call. But feel free if there are any particular questions. Feel free to jump in, and I will be happy to address. You guys all see my slides, right?
Yeah, we can see them.
Awesome. So today I'm going to talk about how far we have become in giving our NLU systems common sense. And as Yejin was mentioning, I think a lot of what I've done in the past many years has had a lot of intersection with the interests of AI too. So it's definitely very exciting to get to talk with you guys about all this research. And Yejin's research as well has been very much influential in the kinds of work that kind of I've pursued. So I'm going to today basically tell you a story, right, which happens to be about my own journey sort of into common sense reasoning. So inherently it's going to be very narrow and through the lens of being grounded in my own prior work. As Yejin mentioned, I'm co-founder of Vernic. We're in a stealth mode, so you can't really find much, unfortunately, about it online. But we are going to be working on the future of decision-making, pretty broad and kind of an ambitious mission. It has a lot to do with NLU and NLP, but not necessarily common sense reasoning. And, we're just growing the team right now. But today I'm not going to talk about that. So a lot of you probably, and some of you who have been on my prior talks, I usually start the same, probably it's now boring that you'll see the exact same thing, but it's just so resonating about how I started working on common sense and NLU that it just can't not share it. So here it goes. I started working in AI through, working in RoboCop competitions and robotics in general, where, I thought I'm working at the cutting edge of AI in the sense that, oh, you're building these multi-agent systems that have to do planning and like reasoning and like, basically play this pretty tactical game of, soccer here. And then somehow I came across this, little book that I was reading back in time that was actually arguing that there's this, paradox that whatever seems to be so easy and fundamentally basic to us as human beings is actually pretty challenging for robots. And the opposite also applies. So something like playing soccer seems so hard to me, whereas ultimately it would be so much easier for robots than some basic NLU problem. So the motivating problem that I sort of was exposed to back in time was this basic anaphor resolution, that in the sentence the monkey ate the banana because it was hungry. What is the core F to it? And of course, as human beings, we know very easily that the answer is monkey. We have this whole background knowledge and common sense knowledge about the attributes of each of these things, and it's just very easy for us to basically know the answer, and even a child would be able to make that resolution. And so fast forward, I always do this with Boston Dynamics, and luckily this was at their 2019 video, and there's now a 2021 video. Just a couple of days ago it came out, where they're dancing to the "Do You Love Me?" and the progress that has been made in control and basically in robotics in terms of how robust these robots are, it's just phenomenal, and still yet to this day. I just double checked this morning. If we put the exact same example that I had come across 15 years ago into Stanford Core NLP, still gets the Core F, wrong. So it thinks it's banana, that is it. And it's just due to the fact that NLU is hard. I don't think I have to tell you guys as the audience here why and how come, but that's like literally what has made me super interested in working in this fundamental problem of common sense and common sense knowledge acquisition and reasoning, just because how hard it is among all the other problems that we deal with in AI. So I told you that I'm going to basically tell you this story grounded in the events that I've been personally sort of witnessing through my work. So I started working in common sense reasoning when I started my PhD back in 2012. And no one really cared about what I was doing. I was, initially working in my PhD, and it was not considered something hot or interesting for people to talk about. But some, stuff started changing in 2015, 16, and 17, which really sort of changed the landscape. So 2015 and 17, we started having new state-of-the-art established on various NLU benchmarks, and the recipe seems to be this thing that someone like Chris Manning was calling the BiLSTM hegemony, where you just encode the input text using BiLSTMs and decode with attention. And although this was deemed to be, like, from the perspective of various people, including himself, the recipe that if you just throw this at any NLP task, you will get the answer. And in my case, I could see that actually you could not tackle reading comprehension tasks that kind of sort of required vast amount of background knowledge, reasoning, or reading actually long established context. So back in 2016, around 2017, we had some renewed interest in common sense reasoning, and even various, there were other kind of pure deep learning people who were acknowledging it as the holy grail of AI, which is what kind of, made me, pretty much empowered sort of to want to pound on the same points that I've been thinking about and working on for the past couple of years, and introduce this, new data set and benchmark, which, basically had to do with having lots of background knowledge and doing reasoning and long established contexts. So a story close test, which we introduced back in 2016, was basically designed to be a story comprehension common sense reasoning benchmark, which goes as follows. There's a context. It's like a short four sentences story. So this is an example. That Jim found an old disposable camera in the bottom of his junk drawer. He began snapping away at everything around him. The counter clicked down to one final photo, and the gravity of the situation began to dawn on Jim. So as human beings, so the task goes as follows: that you read this short context, four sentences, and then you're posed with two alternative endings. And as human beings, it will be very easy for us to know that the the correct ending to the story between these two. So one is Jim took time to decide what he would take a picture of, and the second is Jim took 20 more photos. As human beings, it's easy for us to know that the first one is the right answer, whereas the second one is pretty much unreasonable. And when we introduced this task, and we basically published the paper along with the leaderboard, it was deemed to be a pretty challenging reasoning task, where state-of-the-art was only 65% for many months after the release of the data set. And I'll add the note that intentionally and by design, we did not provide a large direct supervision training data set, because our goal was to push common sense reasoning forward, and we were trying to prevent the task from becoming yet another, kind of pattern recognition and memorization, which is the kind of shortcoming that we were characterizing for other benchmarks that were being beaten. And so things got pretty interesting down the road in 2017 and 18. So as we all know, the dawn of the attention is all you need, and the transformers came at us, and that actually established brand new state-of-the-art on various other supposedly more complex comprehension tasks, where this time around the recipe was fine-tuning. So fine-tuning these large pre-trained transformer-based models on downstream tasks for which there was even a small amount of supervision, which was pretty interesting. So a little bit forward, 2018, very much so based on the same transformers, GPT-1 came out, where on the story close test, they were getting actually 86.5%, which at the time was the basically state of the art. But the question that we were having was, do these models, including now like this new state of the art that is established by GPT-1, again, based on such a small amount of direct supervision, are these models actually learning to transfer conceptual and common sense and board knowledge, or are they basically picking up on some biases that might be in the data set? And this is another very nice work that Yejin and Noah Smith and their students had worked on, which I really appreciated, where they had shown that there were some stylistic biases in the story close test version 1 that we had, which is something that the models can, of course, pick up on and basically, don't do common sense reasoning, but, use these intricacies of the data set to make their prediction. So we were wondering whether or not GPT-1 is doing the same thing. So what we did is that we tested GPT-1 along with a host of other models on the new debiased version of the story close test that we had published at NAACL 2018. And what was pretty interesting is that among all the models that they were testing on this brand new blind data set, without fine-tuning right away, without at all like using the training data set, the GPT-1 trained on the previous version of Story Close was the only model that was still holding its rather high performance. So that was pretty interesting as to, well, perhaps these models are actually learning to transfer some common sense knowledge. So fast forward, 2019 was super exciting for NLP. A lot of amazing like Muppet World kind of work came out, and AI2 with the Elmo model was a pioneer in doing that. And luckily, with the as we grew in having more and more of these models, the community started thinking more about, okay, have we come far enough? And 2018's recipe for transfer learning basically was in full bloom in 2019. The community could see that it's still around. It wasn't like a kind of a bubble that was, that got burst. And as a result, we all started to think more about the weaknesses and shortcomings, and there were all these new, other, pieces of work which were rightfully pointing out that what if we are just having the clever house moment of AI, and I think we need so many more such pieces of work, of course, in the community. And so 2020, as crazy of a year as it was, GPT-3 also was released with its own, hyped up kind of a cycle that it could ride, and doing, various pretty amazing things as well. And like, this is like back in time when it was released, it was right when we were kind of gearing towards raising a round at my new company, and I didn't have time to write a piece about it. Then Greg had sent me given me the access to it to play with, but in my just short time that I had to play with it, I was pretty much amazed at the fact that, look, at the end of the day, setting all the controversies around, setting aside the controversies around whatever are the implications of just this whole paradigm of ever larger models, the fact that they could get pretty high zero-shot performance on the story close test was pretty amazing. So as you see, the zero-shot performance that they were basically reporting on the story close was 83%. And the question is, what does this mean, right? Now we have this ridiculously gigantic language model that has picked up enough background knowledge about the word that it just right out of the box can get 83%. Is this what having common sense looks like? And my answer is that yes, this is a small step forward, of course, towards this very, very high goal that we have in giving machines common sense. And the truth is that we have definitely come a very long way, right? And back when in 2012, probably I personally would not have predicted that we can't even make this amount of progress that we have. But the truth is that we just have to keep moving the goalpost. I think that we have made some interesting progress, but we have to be mindful of what are the implications of us doing well on these benchmarks, which are inherently narrow and by design limited, and just make sure that we keep moving forward by having the bar set higher and higher. So we also, although my conclusion on this part of the talk is that we have come a pretty long way in giving the natural language understanding systems of ours some degree of common sense. We definitely need to work on tackling some glaringly obvious issues that we are still grappling with. One such issue, obvious, something that many people talk about, is the fact that these models make really stupid mistakes. And I would call them brittle, like I guess old school symbolic AI systems were just called brittle, that was the adjective that was used for describing them. I think we can call these models brittle in the sense that you can't really rely on them for deployment in real world, which is something that I personally truly care about, building AI systems that work in practice. And just an example is, I already told you about the story close test, right? The task is to basically classify the alternative ending to a story, but this is an example of just generating it. So I just put in the same story that I told you about Jim having an old disposable camera, and this is how GPT-3 continues it. It says, I'm not going to be able to get more film, I'm not going to be able to get more food, I'm not going to be able to get more ... Jim thought to himself. He looked around his little house and realized that he didn't have much in the way of supplies. So complete, like kind of sort of relevant. You can try so hard to see how it could be a really continuation of that story, but of course it has basically no clue what it's talking about. It's just, is putting things out. And another, example of glaringly stupid mistakes, like I have no idea the story that I put in, like what kind of maybe a Unicode character was hidden in one part of that whole, one character of that whole story, but somehow I decided to just generate in a completely different language, which is again, like, fascinating, right? In terms of how far we have to go for making these systems not brittle. And another quick comment I want to make, which is, is a point that I've been pounding on for some time now, is that a lot of times our presumption of the intelligence of these systems is due to our own intelligence as human beings and our amazing ability on rationalizing almost any random or irrelevant content and deem it creative, which is some way that we've been sort of giving a pass to some of these stupid glaring mistakes by these models. And to continuing on the issues, one was obviously the fact that they're very much unreliable and brittle. The other one that being that, as I mentioned, I've personally worked on establishing various benchmarks. One of them was story close test. But the question is, are these, beating these sort of benchmarks, does this mean real world progress? Does this mean anything that we can basically build on top of? And what is the translation of that into the real world, which is something, again, that I'm super passionate about. I've worked in the startup scene for the past 3 years, more than 3 years, precisely because I believe in wanting to have AI systems that work in outside of the lab setting. So how do we characterize our progress basically based on these benchmarks? And the other is the fact that, of course, there are other implications of these ever larger models that are getting built. And I like this work that came out of AI2 for Green AI, where we should be, I think, very much as a community thinking about the implications of this paradigm of just, basically building ever larger models for the sake of increasing accuracy, and whether or not we're using the right metrics for that, and what that means in terms of the fairness of the entire community. And of course, the major issue relevant to my background is that we yet don't have AI systems that have common sense, even of probably a dog, let alone a 5-year-old kid, which is something that I've been interested in working on personally. Which brings me to the second part of the talk, which is on common sense reasoning, precisely on making this, working basically towards this other cognitive ability that we all have as human beings, which is that we make countless implicit inferences when we read something, piece of text, or when we are told a story. So an example being that even for this very simple story, which goes as follows, that Peppa was riding her bike, a car turned in front of her, Peppa turned her bike sharply, she fell off her bike, and Peppa skinned her knee. So as human beings, when we read this, we construct this pretty coherent representation of what happened and why, which combines not only what we are explicitly reading, but also connecting it to the relevant background knowledge that we have about the world and how it works in general. So one such, coherent construction is the causal chain of events and what happened after what, that basically we just seamlessly can construct in our head. For this particular story, for example, as humans, we know that a car turning in front of Peppa causes her to turn her bike sharply, which in turn causes her to fall off her bike, and then that causes Peppa to skin her knee. And likely, she then asks for help after just, basically falling. Another, such coherent representation that we build is on how different characters' states change, states being like emotions and location, how that changes throughout the story. So one example is that, for example, for this story, we know that Peppa probably went from this state of being, happy and okay, sort of, to being in pain after falling. And in terms of her location state, we know that she was on her bike throughout riding it, and then she falls, which then changes her location to be on the ground. So although we've been, as human beings, we build such, coherent causal models of the situations that we read or hear, very easily AI systems truly remain far from exhibiting such common sense reasoning capabilities. And I characterize the reason for that in like two major bottlenecks. The first one being that we've had historically difficulty in acquiring often implicit common sense knowledge at the scale. And this is, like psych is an example of how when we were historically relying on acquiring common sense knowledge from experts, it just simply does not scale. And the second bottleneck being that we've had difficulty in incorporating knowledge into the state-of-the-art AI systems. And again, psych example being the one that it had its own, psycho language, which was a particular representation. Many people didn't even know where to start with wanting to digest such a language, because it was very much, particular to the way that they had defined what the semantics of, representing knowledge should look like. And I'll like open a window here that it's like so funny that people kind of don't expect like the younger AI researchers who work on common sense to have any clue what psych was, which I think like should just stop talking to anyone who claims to have worked in common sense if they don't have not heard of psych and open psych. Is just something that we have to build on top of all the things that have basically made the progress towards AI until the point that we have basically commented, and just we have to learn, right? We're learning and growing and compounding knowledge. It's just kind of ridiculous, in my opinion, that you would even expect people to give them a pass for not knowing what psych was. I think it's still fundamentally it was a fundamentally great sort of push towards common sense reasoning. So this brings me to GLUCOSE. So GLUCOSE stands for Generalized and Contextualized Story Explanations, which is a work that precisely works on basically tackling the two bottlenecks in AI research that I just outlined. So GLUCOSE is this collection of basically common sense inferences. So given a short story, which we call S, and a selected sentence X in that story, GLUCOSE captures 10 dimensions of causal explanation related to X. And these dimensions are inspired by human cognitive psychology, which cover often implicit causes and effects of X, including events, locations, positions, and other attributes. And I'll add that we spend a lot of time basically discussing what the dimensions of causal understanding should or shouldn't be. We even in our team, we had like cognitive psychologists, we had a philosopher, we had people really from a diverse set of backgrounds who were trying to basically give us insights as to what we are missing and what we are not. So we really tried hard to make sure that we define sort of right dimensions of understanding, which is of course hard, and I'm sure there's so much that we've missed. So GLUCOSE encodes common sense knowledge in the form of these so-called semi-structured inference rules, which we also call mini theories about the world, which are grounded in a specific story. And this is a very sort of unique characteristic of GLUCOSE. We had a lot of work done to basically discover what semi-structured inference rules should and shouldn't be, and why on earth we should even try to acquire knowledge in this particular form. This is kind of interesting. The reason I always actually wanted to work on this work was that when we realized that just common sense reasoning being pushed towards by a benchmark that was kind of narrow in essence, but just predicting the ending to a story, we knew that we wanted to work on explanations, on actually generating causal inference rules, right, to sort of even rationalize why you're choosing a particular ending in a story. So through that, years prior, through that experience, like just thinking about what should be even the way that we represent knowledge, it has been a major problem. And I think that we, after many rounds of studies and pilots, we concluded that it should be in this semi-structured inference rules, which I will talk about more. So let's look at an example. Like I just kind of mentioned what GLUCOSE is, but like not precisely. So let's look at a precise example. So for the same Peppa Pig story, let's say that the sentence X that is selected and wants to be basically causally explained is Peppa turned her bike sharply. So as I mentioned, GLUCOSE has 10 dimensions of causality. Dimension number 1 poses this question, basically. Is there an event that directly causes or enables X? And as I mentioned, the answer should be presented in the form of these semi-structured inference rules. An inference rule meaning an antecedent, a connective, causal connective, and a consequent. So the answer to this question is presented in two forms. The first form is a specific statement, which is as follows. A car turned in front of her causes or enables Peppa turning her bike. And there is a general rule version of the same explanation, which is as follows, that something A turns in front of something B, that is, someone A's vehicle causes or enables someone A turns something B away from something A. And as you can see, this general rule is basically a generalized version of that specific statement, which basically provides general mini theory about the world, whereas the contextualized version is a specific statement that kind of exemplifies how a general rule, such as the one that I explained, could be grounded in a particular context. And as I proceed in the talk, you'll see why this really helps with basically collecting the right kind of knowledge at a scale and getting some kind of knowledge that we know how would be actually used in practice, like being applied in a particular context. So dimension number 2 is, for example, as follows: is there an emotion or basic human drive that motivates X? And the answer in the specific form is Pippa wants safety, causes or enables Pippa turning her bike. And the general form of that is someone A wants safety, causes or enables someone A, moves away from something A that is dangerous. And I didn't, really talk much about this semi-structured inference rule, but as you can see, we have these syntactic slots that get filled in, and as well as these, say a subject slot that gets filled in with, for example, someone A, something A, etc. There could be some attribute clauses that further specify what that general entity is, which are the things in parentheses. And then just quickly, another example, the dimension number 3 is about location. So is there a location state that actually enables X to happen? And in this case, Pippa was close to a car, enables Pippa turning her bike away from the car. And the general statement, general inference rule for that is as follows: that someone A is close to something A, enables someone A moves away from something A. So there are like, two other dimensions that are dimension number 4 being about possession state, and dimension number 5 being about other attributes that enable it. So we have 10 dimensions, as I mentioned. The first 5 are about things that happen before X, and the next 5 are about things that happen after X, and they are basically the mirror of each other. So I'm not going to go over them. And just to wrap this, sort of knowledge model of Glucose up, Glucose is a unique take on how to basically present such often implicit common sense knowledge in the form of these semi-structured general inference rules that are also grounded in the context of a specific story. And so, as I mentioned, there are 2 bottlenecks that I characterize for why we yet don't have AI systems that can build coherent causal models of what they read. One was that we didn't know, or we didn't have ways of, at least back in time, ways of acquiring implicit common sense knowledge at a scale. And given the task that I just outlined for you, it does seem a little like, kind of complex in terms of the fact that it requires understanding the concepts of causality and generalization and these semi-structured inference rules. So the question is, of course, crowdsourcing has been our way of scaling knowledge acquisition in the past couple of years. But the question is, could we actually do that for a task as seemingly complex as Glucose? And the answer is that yes, we spent months basically building this effective multi-stage crowdsourcing platform. And we did many rounds of pilot studies for actually designing an effective platform which was cognitively accessible to crowd workers. This involved, it's just so funny, like I ended up teaching myself how to do front-end dev because it proved to be too much to want to communicate these ideas to another like front-end dev. And so I learned how to do Vue development myself to build these 3 different apps where basically we had this pipeline of a very particular qualification UI to vet the workers and train them, and then the task was done in the main UI, and then we had that in-house review dashboard for giving the feedback and just basically teasing the outliers. So just looking at some examples, looking at some statistics, so far we have basically we collected about 670,000 total annotations, which are covering about 4,800 or so unique stories with 371 workers who participated. And there are some various pretty implicit and script-like mini theories in this data set that I personally really was excited to see coming out. I spent a couple years back in time on working on a script knowledge acquisition, and like we had such a hardship, like knowing how to how could we even acquire script knowledge in a non-supervised manner, and if it's supervised, how do you even go about defining it? So kind of out of this work, through the many causal theories about the work that we've collected, there's some script-like knowledge. So for example, this piece, someone A gives someone B something A, results in someone B possessing something A. Or someone A is careless, enables someone A forgets something A somewhere A. Or this other example that someone A forgets something A somewhere A results in something A is somewhere A, which is again pretty implicit knowledge about like the location of things, for example. So as I mentioned, I've been personally very much inspired by all the prior work that has come out of Yejin's lab and AI2 in general, and it's like been amazing the work that you guys have done on common sense knowledge acquisition. So here I thought that I'll include this slide as just a quick, sort of going over that we did a ceiling overlap, sort of a best effort mapping of the relationships between glucose and atomic as well as ConceptNet. And it's like pretty much the case that there is, of course, some overlap, but there's a lot of knowledge captured in glucose that is unavailable in both ConceptNet and atomic. But of course, atomic is the closest resource in terms of the kind of knowledge that it captures. So the second bottleneck, as I mentioned, was, okay, now that we have basically a way of acquiring such knowledge at scale, how do we even go about incorporating that knowledge into the AI systems, into the state-of-the-art AI systems? And one of the main shortcomings, as I said, in the field has been that, okay, even if I just absolutely need and love the kind of knowledge that exists in these other knowledge bases, like how do I even incorporate it? And classically, like historically, what would have been the case, which is, when I was doing my PhD, for example, we had to think about this, was that, okay, now you have this system that does all the NLP pipeline. Let's say you go all the way from like parsing your sentences to doing even NF4 resolution to this and that. And now the task is to just, okay, how do I inject this knowledge without like doing much of error propagation and compounding. But with the state-of-the-art systems being end-to-end and this potential of basically doing things in a way that we were not enabled to do so before, the question is, okay, how far can we go? So in order to answer this question, we actually set up glucose as an empirical evaluation task. So basically, this is a test bed for evaluating models that can dynamically produce the kind of coherent mental models that I was just talking about when I started the second part of the talk. So on a novel input. So the task goes as follows: this empirical evaluation task. Given a story S, the sentence X that is selected, and the dimension D this time around fixed. The task is for an AI system or for a human to basically produce the glucose specific and general rules. And as a test set, we carefully curated a doubly vetted test set based on previously unseen stories. So these are, brand new novel stories on which our most reliable annotators had the, high agreement. So basically, we wanted to do this so that there are no boundary cases, there are no kind of iffy things that even as human beings, we want to agree on. So this vetting process resulted in a test set of 500 glucose story sentence pairs, each with 1 up to 5 dimensions answered. And for evaluation, we use both human and automatic. So for human evaluation, we actually designed this as specialized UI for collecting calibrated human ratings, which is, of course, super important because you don't want a noisy human evaluation. And for automatic, we actually use corpus level BLEU, which I'm going to talk about. So just a quick glance that for this specialized human UI, which I think was absolutely the key for us to make sure that we are doing a good job in getting reliable, basically scores from the human judges. So quick note on automatic evaluation, as we all know, and you guys have worked on it a lot as well. Automatic evaluation of natural language generation has been an issue for all around. Actually, the reason I personally designed a story close test to be in multiple choice form as opposed to natural language generation was precisely because it's so easy to evaluate, and it's like a reliable way of basically judging systems against each other. But of course, multiple choice tests are inherently easier to be gamed, and the question is, okay, because we don't know how to judge the natural language generations of systems that have often diverse possibilities, we just sort of resort back to doing multiple choice tests. So it's not okay. So we found, luckily in our case, which I'll explain why I think this happened, we found actually very strong pairwise correlation between our human and blue corpus level blue scores on our test set. And this was accomplished through various design choices in glucose. As I mentioned from the get-go, we really had all these criteria in mind for how to design the task so that we achieve different goals, one of which being evaluation. So these semi-structure inference rules that I mentioned, which involves filling these syntactic slots, are actually designed to be evaluable, where the structure naturally limits the format that these basically specific statements and general rules can take. So it's not that the workers and these human beings basically could write anything and everything that they wanted. Actually, we had done lots of pilot studies initially where we showed that if you let people to just explain themselves, right? If you just, all you do is you pose them this question of, okay, what is an event that sort of enabled X to happen, they will write anything and everything. So there's something about putting a structure in place, but it should be actually free form enough that they can express whatever they want without it being all over the place. So semi-structure was the sweet spot for doing that.
Looks like we've lost Nazrin briefly. Hopefully she'll be back.
Oh, she just sent an email. Let me check. Lost the power. So she's logging in right now.
You're on mute, Nazarene.
I'm so sorry. My laptop literally just restarted for no apparent reason.
No worries.
Oh, okay. Let me reshare. Okay. Okay, do you have the slides back?
Mhm.
Okay,
Yep.
sorry guys for the interruption. So anyways, I was just talking about basically our design choices that enable this basically correlation of our BLEU score and human evaluation, which was truly a good cherry on top of the whole glucose cake, I would call it. And so just, going quickly, now, basically this glucose empirical task has a systematic evaluation, which is automatic, that is fast and easily replicable, which is really helpful for building up on the task. So just going over some notable models and results, we actually tried different kinds of baselines, a lot of different baselines, but I'm just going to present the one that, was perhaps at least back in 2020 of the interest, which was the GPT-2 model as a baseline as is. We also trained some models. So we got the same GPT-2 model, we fine-tuned it on glucose, and then we got the T5 model, which is an encoder-decoder architecture, and then fine-tuned it on glucose, and then of course human as a model. So the results of GPT-2 just being that we feed in the story, and then we want to prompt it with some particular keywords to elicit causal information, was that it truly doesn't really have much causal common sense. And we actually spent so much time trying to do our best in giving it a leg up by prompting it with so many different kinds of keywords that hopefully will be a signal in its work to elicit common sense knowledge, and none of them caught, basically. And then, of course, human did the best. The average score out of 3, by the way, these are human judgment scores, which are out of 3. For the specific statement, it was 2.8 out of 3, and then for the general rule, it was 2.6 out of 3. The encoder-decoder was our best performing model, so it got a 2.3 out of 3 for the general rule prediction, and for the specific rule, it was 2.6 out of 3, which was, of course, as you see, there's a gap between the specific statement generation and the general rule, being that general rule prediction is much harder. And so the conclusion here is that the pre-trained language models perform rather poorly at the task and do not show to have any basic common sense inference abilities. And then the second point being that when the same kind of models are fine-tuned on the rich glucose data, they are actually able to achieve pretty high performance in making basically similar common sense predictions as glucose has on brand new, unseen novel stories. And I will add that, so when we did this work, GPT-3 didn't exist, but I did try to do few shot learning as well as zero shot with GPT-3, and it really fails at doing something as kind of complex as glucose. So it wasn't really able to learn to generate these 10 dimensions as is, without using the whole training data set. Of course, GPT-3 is not yet out for fine-tuning purposes. So let's quickly look at some example predictions. Let's assume that this story is as follows. Karen made a pan of lasagna. She brought it to the party. Nobody wanted to eat lasagna. Karen ate it for a week. She became tired of lasagna. So the dimension in question is dimension number 3, which is a location enabling X. So these are the generations. She was in front of a TV, enables Karen made a pan of lasagna, which was generated by GPT-2. If you were in person, I would have asked you to guess which one is GPT-2 and which one is trained GPT-2, etc. But anyway, so, and then the full LM, which is the fine-tuned GPT-2, predicts that Karen is at home. Karen made a pan of lasagna. And the general statement is someone A is in somewhere A, enables someone A makes something A that is edible, which is not bad. But the encoder-decoder does the best job, that it predicts Karen is likely in the kitchen, which enables Karen making a pan of lasagna. the general form of which is someone A is in a kitchen, enables someone A cook something. And humans basically a specific statement and general rules are similar, with the exception that its general rule is like kind of sort of, maybe you can say better, that it says someone A prepares something A that is a dish, instead of saying cooking something A.
Sorry, could I just ask a quick question? So in your evaluation, how often did you find these general statements were repetitions of things in the training sets versus creating kind of a novel general statement? Were they all repetitions?
That's a very good question. We haven't done any systematic evaluation for that, but in the sort of just here and there kind of evaluation that I personally have done, it was surprisingly novel. It was pretty, like, I was really amazed by the performance of the system on novel stories, and novel stories being these are stories that are not seen before. And I would even make sure that the sentence that is trying to make a prediction for, although even if the context is different, the sentence itself was often something that it hadn't seen in the training data, which was pretty interesting. But like something as broad as someone being in the kitchen, of course, happens a lot in the training data, right? Or the fact that being in the kitchen correlates sort of with making things, right, that are edible. But this is sort of one such example. There are many other examples where you can't even say that that's something that has been seen a lot in the training data. With that said, of course, these models are very good at picking up commonalities, right, and making such generalizations. But the part that makes me personally really amazed are the general rules that get generated, which are actually novel, and you can't see that in the training database.
Thanks.
Of course. And then another quick, just, given the time, I want to make sure that we have Q&A time, but just quickly, another example being dimension 6, that is an event that actually X causes or enables. Encoder decoder generates this one, that is Karen makes a pan of lasagna, causes or enable, Karen eats it for a week. And the general form is someone A makes something A that is food, causes or enables someone A eats something A. And then the one for human is, of course, much more elaborate. Let's just read the general rule here. Someone A prepares something A that is a dish, causes or enables someone A takes something A to something B that is an event. And we won't have time to talk about this, but in our paper we talk elaborate on what it even means to have to hit the right level of generalization. Of course, it's like something that even human beings won't agree on. So that's like, of course, an ongoing kind of line of work for itself. So this very, very quickly, I just love talking about this. This is a question I've gotten so much when I've been giving this talk in the past couple of months, that people ask that, okay, for that kitchen example, for instance, it's not that the person was actually making the food in the kitchen. For all we know, maybe Karen was outdoors, making that food for the party in her backyard or something, right? And is it that we can call these common sense reasoning systems as the systems that just hallucinate? And my answer to that is that, well, actually, even as human beings, turns out we are not just passively perceiving the world, we are actively generating it, meaning that what we actually even perceive with our sensory input kind of data is all grounded in the context of what we know from past, which are priors. And that helps, basically turns out that helps our brain make best guesses from what is actually happening. So I love this quote from this cognitive neuroscientist, Anil Seth, that says that hallucination is actually uncontrolled perception, but in turn, perception is also uncontrolled hallucination. Meaning that pretty much anything that we actually perceive is our common and sort of just understanding of what we take to be the truth versus not true, just because we accept it to be the truth. And with these illusions being that we've all seen a good example. So the truth is that the AI systems are also making their best guesses, right? Given all the prior that they have. Of course, with providing more context, more details, these are defeasible, and you can, of course, make different kind of predictions. But turns out, even as human beings, this is what we do. We make our best guesses about the world and what is happening and what we perceive. It's not necessarily something that is happening. So to conclude this, last part of the talk, we proved the following through the glucose work, that a promising new recipe for giving machines common sense is to use high quality common sense knowledge, such as glucose, for training neural models that have pre-existing lexical and conceptual knowledge. And I would argue that the value of such trained models that can kind of dynamically generate glucose dimensions on any novel input is so much more than any static knowledge base, which will be narrow by inherently, because how much can you go about like collecting such pieces of knowledge. So I think this is the new kind of common sense knowledge base paradigm that is dynamic, and this is something that Yejin's group has also worked on a lot. And so with the, I thought this is timely to somehow use Stacy's quote on why, with the, basically last night's election and the presidential election, that jumping from what to do without knowing why is pretty meaningless. And of course, Judah's quote on AI as well, that to build truly intelligent machines, we should teach them cause and effect. So I think that working on causal explanation of what we read has to be a major part of any AI system that wants to be deployed in real world. And so just to wrap it up, I started the talk showing you this picture. I think that I've sort of started my journey around here, and maybe we are getting closer to even being in the vicinity of the mountains that we are trying to climb, and the actual peak is right there. So I think we've made a reasonable amount of progress, but we have a very, very long way to go. And thank you guys for listening.
Great talk. We have very little time left for QA, unfortunately. In part, Nasreen has meetings coming up right away, I think, but maybe we can have a one.
You guys, right? I'm so sorry for my laptop. That was really ridiculous. So we lost like a couple minutes with my technical difficulty.
Yeah, maybe one or maybe two questions, if quick. Or I can ask first. So you mentioned earlier that the overlap across different common sense knowledge resources are very little. And I thought it's somewhat surprising in that at least the dimension 2 was about emotional precondition or emotional causes or motivations, which is a prominent dimension in atomic as well. And is the low coverage because the lexical overlap didn't match enough for particular phrases and sentences? If that's the case, actually, because glucose is defined over concrete situations, as opposed to atomic is defined over generic events, maybe it makes a little bit more sense to also look into like how COMET predictions overlap with what's in the glucose.
That's a very good point. It would be lovely to compare COMET to glucose, as I was saying, like just having dynamic systems is just by far more reasonable and better, right, in every aspect than these static knowledge bases. So what we did, which is what I think you also did in your paper for comparing to ConceptNet, is a best effort mapping, right? And the goal of that is that just I think that you can find the details in the paper. We discussed that what we've done is, because lexical matching is kind of, dumb, but what can you do? We had even taken all just the verbs, right, in each sentence sort of from both the data set and try to map that. And I think that the low coverage, you're right, that in terms of the knowledge model, so enabling emotions, for example, is something that Atomic also nicely covers. But I think it just comes down to just, this just random selection that we did in terms of what it may or may not have had on the other side. But yeah. But this is definitely, I would love to see how the dynamic models actually compare. That would be the best idea for sure.
Yeah, so in our new paper, COMET 2020, Atomic 2020, we also show the symbolic knowledge graph comparisons as well, but we focus more on the neural representation comparisons that result from any of these resources, because in the end, that's how anybody uses any of these resources today, which is not as a static graph, but as training samples for neural models. Any other quick question? One more from the audience.
Nazrin, do you have any sense of how complete glucose is? Do you feel like it's a drop in the ocean, or is it, covering 30% of the knowledge you'd need for general story comprehension?
I'm sure it's a drop in the ocean. Like, my God, like I think I've heard Yejin make the same point, that it's just, there's no way, right, you can claim that you've covered even a portion of this vast knowledge, right? In terms of the knowledge model, we've really tried our best to include whatever these crowd workers basically can grasp within one task, right? Cognitively, something that they won't get confused. We started having distinctions between enable and cause, for example. We started wanting to capture also script-like, right? We started wanting to capture before-after relationship. We had 18 dimensions originally, which then got boiled down to these 10 that you see because of the rounds of iteration that we had with these pilot studies with our crowd workers. So in terms of knowledge model, I think we did our best in including whatever is sort of digestible by workers. But of course, at the end of the day, this knowledge is captured by iterating basically over 4,000, they said 800 or so stories, right? It's a drop in the ocean. And also, Common Sense knowledge is so vast, right? This is only causal explanation kind of knowledge in the context of events and states, right? There's so much more about physical knowledge and social knowledge, norms, etc., that are not covered.